Hi, I'm Robert Jean-Pierre. Today I'm presenting my final project, Empirical Investigation of the Rademacher Complexity and Margin-Based Generalization Bounds in Neural Networks. The goal is to test whether classic learning theory actually explains what we see in deep learning. Classical theory says models with more parameters should overfit and generalize poorly. Modern deep networks completely contradict this. They have huge numbers of parameters, fit the data perfectly, and still generalize extremely well. So the basic question is classical theory still useful or does it break down in its regime? Here is a simple example of the problem. Same logistic regression model, same data distribution. On the left, labels are clean. On the right, I added 15% label noise shown as yellow points. The right problem is 176 times harder in terms of generalization gap. We'll see whether theory can tell these two apart. This project is built around three questions. How loose are classical generalization bounds in actual numbers? Does Rademacher complexity track problem difficulty, easy versus hard? Why do overparameterized neural networks generalize better, not worse? I use two kinds of data. First, 2D Gaussian blobs, one clean version and one with 15% labels flipped. Second, a real task, MNIST 3 versus 8, almost 9,000 training samples in 784 dimensions. For models, I compare logistic regression with 785 parameters to a neural net with 100,609 parameters, which is about 128 times larger. Everything is implemented in Python, and I use PyTorch on an RTX 4090 GPU. Logistic regression has 784 input plus a bias. The neural network has one hidden layer with 128 ReLU units and a sigmoid output, giving about 100,000 parameters. Both are trained with Adam, standard binary cross entropy, batch size 64 for up to 20 epochs. To estimate Rademacher complexity, I use Monte Carlo method, train 30 to 100 models on random plus or minus one labels and measured how well they fit pure noise. To quantify uncertainty, I use 1,000 sample bootstrap confidence intervals. To test differences, I use 10,000 sample permutation tests. All experiments use fixed random seeds, so they're fully reproducible. Finding one. Classical bounds are extremely loose. For clean synthetic data, the bound is 150 times too loose. For MNIST logistic regression, about 25 times. And for neural net, roughly 266 times. In the most extreme case, a model with 99.1% test accuracy gets a bound that predicts 240% error, which is impossible. So bounds are mathematically valid, but useless for any practical decision. This figure shows the bootstrap estimates. On the left, the Rademacher complexity for clean and noisy blobs is almost identical with overlapping confidence intervals. On the right, the error bars are very narrow, so our estimates are precise. At the top, the permutation test gives a p-value of 0.43, confirming that the small difference we see is not statistically significant. What does 266 times looseness mean? The bound predicts about 53% error, while the actual test error is only 2%. This happens because the theory makes worst-case distribution-free assumptions and effectively takes a union bound over all 100,000 parameter models. So in practice, you can't use these bounds to choose model or predict performance. The guarantees are simply too pessimistic. Finding two, Rademacher complexity does not predict problem difficulty. For clean blobs, The generalization gap is 0.008, an extremely easy problem. For noisy blobs, the gap is approximately 0.147, 176 times worse. Yet Rademacher complexity are about 0.0505 and 0.0550, only about a 9% difference with overlapping confidence intervals and a p equals 0.43. So the complexity measures barely move while the gaps explode. This bar chart makes that contrast clear. The blue bars, Rademacher complexity, are tiny and almost identical. The orange bars, generalization gaps, are hugely different. So the standard complexity measure is basically blind to how hard the problem is. I repeated this across 9 different experiments, different sample sizes, data sets, and dimensions. Here, the Rademacher complexity is on the x-axis and the generalization gap is on the y-axis. The Pearson correlation is R equals negative 0.124 with a P equals 0.75. So statistically, as I mentioned before, the Rademacher complexity has no predictive power for generalization in these experiments. Finding 3 looks at the parameter count paradox. Logistic regression has 785 parameters. The neural network has 100,609, about 128 times more. Classical theory says the big model should overfit and generalize worse. Instead, the neural net reaches 100% training accuracy and 98.99% test accuracy with a generalization gap of 0.009, about 37% better than logistic regression. So here, more parameters actually do help. This plot compares theory and reality directly. The dashed line is what theory predicts. As parameter count increases, the generalization gaps should go up. The orange points are what we observe. As capacity increases from 785 to over 100,000 parameters, the gap actually goes down by 37%. So in this setting, the core qualitative prediction of classical theory is actually backwards. For neural net, the bound becomes completely vacuous. If we estimate its Rademacher complexity, it would be very large because a 100K parameter network can fit random labels easily. Plug that into the bound, gives something like error less than or equal to about 100%, while the truer error is only 2%. So the bound is technically true, but tells us nothing we didn't already know. Finding 4 explains why the neural net still generalizes. Implicit margin maximization. Training doesn't stop when accuracy hits 100%. For epoch 1 to 10, accuracy rises from 94% to 100%, and the margin goes from 5 to 8.9. From epoch 10 to 30, the accuracy stays at 100%, but the mean margin grows from 8.9 to 18.1 to 78% margin growth after perfect fit. And about 60% of total growth happens in that phase. Compared to logistic regressions, mean average of 6.5, the neural net reaches about 15.7, nearly 2.8 times larger. This plot shows that training behavior over time. The green curve is the neural net's margin. The vertical line marks the epoch where training accuracy first hits 100%. After that point, the accuracy is flat, but the margin keeps increasing, ending up 78% higher by epoch 30. The purple dashed line is the logistic regression margin, and the neural net stays well above it. Gradient descent on cross entropy is implicitly pushing the decision boundary to increase its margins. These histograms show the full margin distributions. For clean synthetic data, margins are tight and large. For noisy labels, there's a wide spread and lots of negative margins. On MNIST, logistic regression peaks around 6.5%, but the neural net peaks around 15 with no negative margins. That means the neural net is making more confident predictions farther from the decision boundary, and that geometry explains its generalization. Why does classic theory fail? Putting things together, theory and reality are modeling different things. Classical theory assumes all parameter settings are equally likely, capacity is purely a liability, and analysis is worst case over entire hypothesis class. In reality, gradient descent has a strong implicit bias. It favors low norm, large margin solutions, and only explores a tiny slice of the space. That's why we see huge gaps between bounds and actual performance, and why the correlation between Rademacher complexity and generalization is essentially zero. Well, like R equals negative 0.12524, sorry, and P equals 0.75, to be exact. Margin-based analysis does better. The margin bound says that generalization gap should scale like 1 over the square of the margin. Empirically, clean blobs have large margins and tiny gaps. Noisy blobs have negative margins and large gaps. On MNIST, logistic regression has smaller margins and bigger gaps, while a neural network has larger margins and best generalization. So margins capture problem-specific geometry that pure complexity measures miss. For theorists, the takeaway is that worst case, algorithm-independent bounds aren't enough. We need optimization-aware theory, like things like, pack-based stability, compression, or NTK styles analysis that reflect what gradient descent actually does. For practitioners, the message is don't fear large models by default. Parameter count alone doesn't determine generalization. The quality of the decision boundary and the margins do. Empirical evolution Empirical evaluation is still essential because current theory is far too pessimistic in this regime. To wrap this up, classical bounds in these experiments are between about 150 to 266 times too loose. Rademacher complexity shows no meaningful correlation with generalization. R equals negative 0.124, P equals 0.75. Neural networks with 128 times more parameters actually generalize 37% better, and we see 78% margin growth after perfect training fit. Margins and implicit margin maximization of gradient descent explain generalization far better than static capacity measures. Overall, classical uniform convergence theory is mathematically sound, but too pessimistic to explain modern deep learning. So we need new optimization-aware frameworks. Thank you.